Right. So we thought we would start with a little Kahoot. I've only got 8 questions just to get yourselves warmed up and see if you want to have a go at that. So it's just 8 questions. If you want to split the screen or go on there. Let me see if I can share my sound. There we go. Move that over there and start. Right, so there's the game pin. If you just want to log into Kahoot, hopefully you've all done Kahoot before. I think we did this yesterday, didn't we? Tejas, you weren't here. Have you done Kahoot before?
Yes, I have. I have.
Yeah, okay. So it's only 8 little questions and they're all on A2 content. We hear the music now. You have shared it, okay. Okay, perfect. Was that everybody? We got anybody else joined since? Yeah, just make a start. Just get us a little bit warmed up, only take a few minutes. So, do we multiply the A and B together? Is that true or false? It's going to be true, isn't it? Then logs work kind of the opposite way to indices. When you've got the same base and the powers, you add the powers. When we've got logs, when we're adding them, you can multiply the numbers. Oh, here's Mia. Now it's base 2. If you replace that 8 with 2 to the 3, that's going to help you. So replace that 8 with 2 cubed and then sort the indices out. 2 cubed 3 times 10 would be 2 to the 30, and the answer to the log is always the power. So that's going to be 2 to the power of 30 is equal to 8 to the 10, which is 2 cubed to the 30. So you see how that's working with the 8, just put it as a power of 2. So well done, who got that right? Did you do it on your calculator, Ritesh, or did you do it the way I was suggesting there? Did you do it on your calculator?
No, the way you suggested.
Yeah, okay, cool. Yeah, the answer to a log is a power. Right, sec squared. Who knows their identities? You've got the sine squared plus cos squared is equal to 1. And then if we just divide through by cos squared throughout, we're going to get one of those. Are we going? Mia, I think if you're with us, the game's there. It's only 8 questions. We did a Kahoot yesterday. This is a short one. The game pin's there, but if you can just join in, hopefully you can see the screen. Can you see the screen, Mia?
Yeah, I'm just trying to get on.
Yeah, don't worry. Just do the questions because it'll be over before you know it. You could get on if you want. But e to the 4x. When we integrate, we're going to do it by reverse chain rule. So e integrates to the same thing. And then what's going to happen to that 4? You're going to have to compensate for the fact that a 4 will come from the chain rule when we differentiate. So we need to get rid of that. So it needs to be a quarter. Always when you're integrating, you more often than not divide. Remember, when you integrate, you add 1 on and divide by the new power. So you need to be thinking of what I need to do to compensate for what will come from the chain rule. So I'll take just back up there. Good. So what we asked to do with this, f inverse, so f to the minus 1. So we times by 5 and add 4. If we're going to do the reverse of that, you'll have to do BIDMath in reverse. You will be taking 4 and then dividing by 5. Yeah, so we're better with that one. Taking 4 divided by 5 is going to be green. Well done, everyone's getting that. 2 functions. We're going to be asked to do a composite function. So in maths, we don't read stories, we do what's nearest first. You need to do G first. G tells us to square And then F tells us to double the input and add 1. So you need to do 2x squared and then add 1. So it's going to be the blue. What did we put? Yellow. Yeah. Oh, no, I got that one. Differentiate. So we're going to use the chain rule. Power down, take 1 off, leave alone on the inside, and then multiply by the differential of the inside. So power down 7, take 1 off, and then you're going to multiply by 3. So yeah, I'm good at that. So going to be 21 on the front. Well done. Right, last one. Differentiate. You're going to differentiate this using the chain rule. When you're using the chain rule, differentiate with respect to the outside and then multiply by the differential of the inside. So cos differentiates to minus sine. So we should be getting minus 4 sine of 4x minus 1. Good. Right, who's on our podium? Ritik, well done. Pages. Go to the top. Ritesh. Well done, guys. So that's got us a little bit warmed up. Let's get on with our stuff for today. So we're going to be looking at differentiation and integration today. If you want to join in and unmute, that's fine. If I call on you to speak and you would rather just put it in the chat, that's fine. If you want to ask anything, just put your hand up on the chat. That's fine as well. Just do whatever you're comfortable with. So this is me. For those who don't know me, that's me with my giant dog, Mabel. So we're going to do some maths revision for calculus. And when we're doing calculus, we mean we're going to be differentiating, or integrating. So the different things that we're going to be looking at, we're going to use the chain rule. The chain rule is when you've got a function of a function. So you just had some of them in that Kahoot. So if I had y is equal to sine squared 3x, that's actually a function of a function of a function. So you need to be thinking, what happens to x first? I would times it by 3. Then I would take the sine and then I would square. And when you're differentiating using the chain rule, you differentiate with respect to the outside, leave alone, and then work your way in. So I would power down, take 1 off, and I've left alone with everything else. Then I would differentiate with respect to the sine, which is going to be cos 3x, and then differentiate with respect to the 3, which would be a 3, which would change that to a 6 on the front. Okay, a product rule is when you're going to be doing y is equal to uv, when you've got two functions that are times together and they both involve the variable. Now, you will have been taught different things. I say, because it rolls off your tongue a little bit better, it's going to be first differential of second. So v dash is differential plus, oh, there's another one. Let's just let them in. Plus second, which is v differential of first. Now, because you're adding them, I know, Ritesh, you do it the other way around, don't you? When you're adding them, doesn't really matter. I always remember it that way because when you're using the product rule, product means times, and times is the first thing you ever learn before you learn to divide. And so the product rule always starts with first differential of second, and it's a plus, and it's all on one line. That's the easier one, and that kind of lends itself to when we're doing a quotient, which is u over v, which starts the other way around. That is going to be bottom diff top minus top diff bottom all over bottom squared. So they kind of just roll off my tongue rather than writing them down. You do get the quotient rule on the formula sheet. You don't get the product rule. So max and min, that's where dy by dx is equal to 0. Some trig. So on your calculator, you get your sine, cos, and tan. I always used to remember when I was your age, differentiating sine, that's the one that goes to cos, because we learn to differentiate first, and that goes to cos, and then you just get that chain. Cos goes to minus sine, which goes to minus cos, which then goes back up. And that's how we differentiate. So going that way down for differentiate. And then when we integrate, we're just going to go the opposite way. And then tan, you learn how to differentiate tan later, because tan is sine over cos. And we do that by knowing that we've got the function over the differential on the top over the function, and the differential of tan goes to sec squared x. Implicit is when you have x and y, or y not the subject. So you might have like x squared y plus xy is equal to 5. So y isn't the subject, and you will not have known it at the time when you first learned how to differentiate. But when y is equal to, say, 3x squared, when you differentiate this side, you write dy by dx, and then you'd power down 6x. So when we differentiate, when it's implicit, whenever you differentiate with respect to y, you have to times by dy by dx. Rates of change, whenever you see the word rate, you're going to be looking that something is changing with respect to time. So it's dt. And then often you can make chains. So you have to think of what variable and what the linking variable is involved, and do it like that. Parametric is when you have a third variable. Often it's t, or if there's angles involved, it's theta. And if we're wanting dy by dx, we have to make a chain. So it would be dy by dt times dt by dx. Now the dy and the dx, all of these differentials, there's derivatives, they are not fractions, but you can treat them like fractions. So if you get what stands for these two, the dt's will cancel, and we are just getting the dy by dx. So they're all the things we're going to have a look at first with differentiation, and then we'll do the same again and have a look at integration. So first of all, 9 marks. These are all past paper exam questions that I'm using. We're going to be differentiating here, and we can see that we've got a product. So what are we going to use? Because we've got a product, we're going to use the product rule. So dy by dx. So remember, it is first differential of second. So first differential of ln. Now ln of 3x, this is a function of a function, because we've got to differentiate with respect to the 3x and with respect to the ln. So remember what we said, you differentiate with respect to outside first, so that will be 1 over 3x, leave alone on the inside, and then because you had a function on the inside, you then times by the differential of that. So whenever you have a multiple of x on the inside, these 3's are actually going to cancel. So that's first differential of second plus second differential of first. Now, because differential of first is a 2x, I'm going to put that on the front, ln of 3x. I'm not going to put the 2x here, because then it might get mixed up with the 3x. I'm just going to put that on the front there. And then we'll tidy up. So we'll have an x here, will cancel, and we'll just get x plus 2x, the ln of 3x. B, this is a quotient, so we've got a u over v, so dy by dx is equal to
part A. What did you do with the square root of the x there?
I've just cancelled, because I've got x squared on the top and I've got the x on the bottom, so just cancelled, because I've got x times x and x on the bottom, and they will just cancel.
Okay, thank you.
Yeah, okay, brilliant. Yeah, just butt in and shout out. There's probably a lot of us. Let's just see how many. We've got 9 now. So yeah, if you want to say anything, just put something in the chat, and then you can put your hand up on the chat, and I can just see it there. Right, the next one is going to be a quotient. So the quotient rule, you do get that on the formula sheet. It's going to be bottom differential of top. Now again, we've got a function of a function, which we need to use the chain rule. So chain rule, we differentiate with respect to the outside first. Differential of sine is cos, leave alone on the inside, and then multiply by the differential of the inside, which is going to be a times by 4. So we'll put that on the front. So that is bottom differential of top, and then minus top sine 4x differential of bottom, which is 3x squared. And then you've just got to remember when you're doing the quotient rule, all over bottom squared, which is going to be x cubed all squared, which I would write as x to the 6, because you're just going to multiply. Now, would anybody tidy up there? We could possibly take what's the common factor here and here. We would take an x squared out, and then that would be 4x cos 4x minus 3 sine 4x all over x to the 6, and then I could cancel them, and that would reduce down to 4. You couldn't really do anything more than that, but then you know, if you see a question like this, when you do your exam, about 50% will be routine stuff that you can just get on with doing. Often it's easy to use the quotient rule, product rule. Sometimes it's hard manipulating what you got when you've used the quotient rule to get it in the form that they want. But is everybody okay with those two? Just an easy one to start with, maybe. Just using the product rule and the quotient rule. Okay, next one. Now here we've got x and we've got y over here, and it's asking us to find dx by dy. So things are a bit topsy-turvy, but we can still cope with that. We've just got to go dx by dy, and then we've got to differentiate this time because we've got the y on the bottom with respect to y. So we can see we've got a chain rule again. So what happens to y first? It's times this by 3. Then you will take the sec, and then you will square on the last thing. So you work outside in and differentiate with respect to the squared. So we would power down, we would leave alone, we take 1 off, so it would go to 1. So that is me differentiating with the outside. Then we would differentiate with the next thing that's on the inside, which is sec. Sec differentiates to sec 3y tan 3y. And then finally, we would differentiate with respect to the one on the inside, which is the 3y, which would be times by 3. So we'd just change that on the front to a 6. So altogether, we have got 6 sec squared 3y tan 3y. So when you're doing sec, the powers of the sec stay the same. So then it's asking us to show, hence show. So when it says hence, you've always got to use what you've already found out, dy by dx. And we've just got dx by dy. So we need to turn that upside down. So we know that dy by dx is going to be just that upside down. So it's the whole of it, 1 over 6 sec squared 3y tan 3y. So how are we going to get from that to here? We need to go back to the beginning because we need to look where we need to go. This is all in terms of x, and what we've got at the moment has got y's in. So up here we can see that x is equal to sec squared 3y, and we have got 6 of them. So this is going to be 1 over 6x, and then what we're going to do with this tan 3y. Anybody got any ideas about the tan? How are sec and tan related? What can we do?
And squared
Second
plus
y
1.
over time.
Yeah, do we all know that sine squared x, or we're in y, plus cos squared y is equal to 1. So quickly, if you can't remember them, you can just quickly, to get some tan on the go, divide by cos squared y. So that is going to give you tan squared y plus 1 is equal to sec squared y. And so tan squared y is equal to sec squared y minus 1. So tan is going to be, I just need to take the square root. So this is going to be my x minus 1, because if I just put a 3 in front of those, I would get a 3 there. So now I'm going to get my x minus 1, and then instead of doing the square root, I've got to the half, which is what they've got there. Everyone understand what we've done there? We okay?
Back to A for just a second. How did you
Yeah.
get this right at the front?
The 6 at the front. First of all, when you're doing the chain rule, you recognize that you're using the chain rule because you've got a function of a function. How you know you've got a function of a function is because you've got lots of things happening to y, and they all need to be differentiated with respect to. So you've got here 3y, you've got the sec, and you've got the squared. They're all things that need to be accounted for when you differentiate. And what you do is you start from the outside. So what would happen to y last? Like if you think about rules of BIDMAS, we would times by 3, then we would take the sec, and then we would square. So you need to power down, and then we would leave alone. Then you differentiate with respect to sec, which is sec tan, and then you'd finally differentiate with respect to the fact that it wasn't just y, it was 3y. So you times by 3, and I've just put that on the front and got a 6.
Okay, thank you so much.
Does that make sense? Okay, cool. All right. How about C then? We've got to do the second derivative. So now, because we're in terms of this, we can do the second derivative. Now, even though it is here, I said before you would maybe use the quotient rule if you've got a u over v. I think probably the best way to do this is to use the quotient rule even though you've got that 1. So the quotient rule is bottom diff top minus top diff bottom all over the bottom squared. So d2y over d.
I am calm. Get out.
Can you not talk to me like this? Eh? Can you not talk to me like this?
I can't hear you.
You can't hear me. Behave yourself. Okay.
I'm really sorry, but I can't hear you.
You'll hear. Soon you'll hear.
I can't hear you.
Okay, could you just mute so that we can carry on? What we've got here. Sorry. Right, second derivative. So we're going to go bottom, which is 6x x minus 1 to the half. Now differential of top, because tops is just a number, that's going to differentiate to 0. So it's bottom diff top minus top, which is just 1, differential of the bottom. Now differential of the bottom is a product, so we need to use the product rule even though we're in the quotient rule. So the product rule says that there's going to be 2 terms, because we're going to do first diff second plus second diff first, and it's minus all of those. So we're going to need some brackets, and it's going to be first 6x differential of the second, which is a chain rule. So we power down x minus 1, take 1 off. And then, so that's first differential of second plus second differential of first, which is going to be 6x minus 1 to the half, and then that would all be over bottom squared, so that would be 36x squared times x minus 1 just by itself, because we're going to square that, so that will get rid of that half. And then we would just tidy up, so 0 times all of this is going to be 0, and then we just need to have a think about what we would do with this second lot here. So when you've got 2 things here that are being added together, what we can do is factorize. If you think of like 3x squared plus 6, you can take out a factor of say 6x. You can take out a factor of 3x, and then it would be x plus 2. So what you do when you're looking at what to take out is look at the lowest power. And what we've got here is x minus 1 to the minus a half and x minus 1 to the half. And we've also got a 6 in the numbers. So I can take out, I'll take out a minus 6 and then an x minus 1 to the minus a half. And then inside, I will then get a half x, and then I'll have taken that out, so that's fine, the 6, and then what will I need to times by to get to this? I will just need a plus an x minus 1. And then I'm all over 36x squared, x minus 1. Does everybody understand what I've done there? I've taken 6, this out, and an x minus 1 to the minus a half. And then what will happen with the 6 and the 36? That can cancel down. So I'll just get 6 there. And what I'm going to get on the top when I times this out, this 6, this x minus 1 to the minus a half, the minus will take that underneath. So we're not going to have enough room here. So altogether on the top, this minus will go in here, and I'll have a half x plus an x, so that's going to be 3 over 2, but it's going to be minus, and then I'll have a minus 1, but minus 1 is going to be 1. So I'll have 1 minus 3 over 2x all over a 6x squared, and then an x minus 1. When I've taken this to the minus half down, it's going to join in with this 1, and we're going to add them together, and that's going to be 3 over 2. Now what I can do on the top just to tidy up is take that line all the way across. So in order to make that whole one over the common denominator of 2, it's going to be 2 minus 3x, and then that 2 on the bottom can join in with this 6 all over a 12 x squared, and then x minus 1 to the 3 over 2. So as I said before, actually applying all the rules is usually okay. It's manipulating, see it said, into the simplest form.
Could you go from the third to last step to the second to last step again? I just didn't see how that happened.
See here, this numerator?
Yeah.
Yeah, so when we've got 1 minus 3 over 2x, often like just take bits of the sum to the side and do them separately so it's not all bogged down in that. To make this 1 have the common denominator, I can just say that this is going to be 2 over 2, which is 1, minus the 3 over 2x, and then I've got 2 minus 3x all over that common denominator. So if I want to just take that line all the way across, I need to give this 2 here, a 2, and then I can take the 2 all the way across. So then this 2 here, because it's underneath, can join in with this 6, and that's where I get the 12 from. Hopefully that's made sense there.
Yeah, that does make sense. But how
Okay.
about from the step before that one?
The factorizing business.
Yeah.
Yeah. So you need to be able to cope, because you understand this when we factorize, that's like an easy thing. So when you're looking for what's a factor, if I just get rid of that first bit, because that's all times by 0, so we've got none of that, haven't we? What you've got here is what's common to both of these terms. You've got this term and this term. So they've both got a 6. So I'm going to take out minus 6, and then this bracket and this bracket, you look and see what is the lowest power. Minus a half is the lowest power. So I'm going to take 6, x minus 1 to the minus a half out. Okay, so when that's out, what do I need to multiply to get back to all of this term? I've got the minus, I've got the 6, I'm going to need half x. And then I've already got that. So that's that term done. Are you following?
Yeah.
Yeah. And then what will I need to get to the next one? I've got a 6 on the front. The minus is going in, so that's fine. And then how am I going to get to the x minus 1 to the half? All you need to do is say plus x minus 1 to the 1. And remember, when these things times together, what's going to happen to the powers? You're going to add the powers. So if the powers are at minus a half and you add a whole one, if you think on a number line, you're at minus a half and you need to go a whole one, that will take you to plus a half. So out will come this half. So we need to add those powers. And then what I did was put this half x and this plus x, that's 1.5 x, and then the minus 1. But then the minus on the front turned that 1 to a plus 1, and then we had the 3/2x. Does that help a bit?
Yeah, it does. Could
Yeah.
I just ask about the power thing again? When do you times the power?
What do you mean times the power?
So why did we have to, are we expanding it again after
No, you're factorizing, and then when you factorize, you've got this thing on the front which is operating like that 3x, and then you can just add these together.
Oh, okay.
So you're factorizing, yeah. So this is what you have to do sometimes to get it in simplest form.
Okay, so what did you write down there about the minus half plus 1?
That was for the powers, because this minus half plus 1 is going to get us back to this half.
Oh, okay.
Yeah, okay. All right, let's have a look at the next one. This is actually similar to the one we've just done. We've just done a dx by dy. So let's maybe leave that one and have a look at the next one. We're going to run out of time. What are we on? Okay, so here we've got a curve, C, and we've got, it is a product. For part A, it says find the x-coordinate of the turning point. So what do we know about turning points? Then the gradient is going to equal 0. So as soon as we see turning point, we know we're going to have to differentiate and equate it to 0. So we're trying to find the x-coordinate of the turning point and give our answer as a multiple of pi. So we need to do dy by dx. And we've got a product. So it is first, so it's e to the x root 3. Differential of second, to sine 3x, we again need to use the chain rule. So differentiating with respect to the outside, which is cos 3x, leave alone on the inside, and then multiply by the differential of it. So maybe just put the 3 there so it doesn't get confused with that power. So that is first differential of second plus second differential of first. So I'm going to put second and then do the differential of first here. When we're differentiating e to the x root 3, we're going to use the chain rule. E to the x differentiates to itself. So we're going to get x root 3, but then times by the differential of that inside function, we're going to get a root 3. Everyone okay with that, with using the product rule? Yeah. Okay, now at a turning point, so at TP, dy by dx is equal to 0. So what can we do now, Georgie? Any ideas what to do here? Now you've got to think of what this function involves. It involves e's and it involves sine and cos. Sine and cos do actually allow you to go to 0. If you think of the e graph, does that ever go equal to 0? It doesn't. So what we need to do here is factorize, and we can take e to the x root 3 out. And then this is an easier factorizing, isn't it? We're going to have 3 cos 3x plus root 3 sine 3x is equal to 0. So you know when you try to solve a quadratic, you put it into 2 brackets equal to 0. Same idea, factorizing it and putting it as 2 things that times together equal to 0. The whole purpose of doing that is that e to the x root 3, does that equal 0? Well, any E graph is not going to equal to 0. So that's going to not give us any solutions. It's only going to happen when this thing in the bracket equals 0. So you've got 3 cos 3x plus root 3 sine 3x must equal 0. And what will we do here? Maybe take that to the other side and get root 3 sine 3x is equal to minus 3 cos 3x. And then we're just going to cross multiply, get sine 3x over cos 3x is equal to minus 3 over root 3. So sine over cos, we all know what that is. That's just going to give us tan 3x. And then what will we do here? We can rationalize the denominator. So root 3 over root 3, that's going to give us minus 3 root 3. Those denominators are going to give us 3. So the 3's are just kind of cancel and it's minus root 3. Now on your calculators, or maybe you know your special triangles. Anyone know the special triangle that involves 30? Sine 30 is a half. And then by Pythagoras, this is root 3. So if this is 30 and that's 60, then you're going to get tan 60 is equal to root 3. Now your tan graph goes like this. So when we're doing tan 60 here and getting the positive root 3, your tan graph down here, if we go minus 60, that's going to give us the minus root 3. So either on your calculator or you just kind of know your graphs and your special triangles, that's going to tell us that 3x is going to equal minus 60, but we're in radians. So we all know that pi is equal to 180. So pi by 3 is equal to 60 degrees. So 3x is going to give us minus pi by 3. And so x is going to equal minus pi by 9, just taking that 3 down. But we want p. So we found this place here because it's minus pi by 9. So we need to go back to our tan graph and see where's the next place where we're going to have a 60. Well, the tan graph, after it's got here to pi by 2, is going to come like here. And if we go 180, which is pi, and come back the pi by 3, which is the 60. So a whole pi minus a third is 2/3 of pi. So, and then we divide by 3 again, and that's going to give us 2 pi by 9. So this is good because we want a multiple of pi. And so we recognize that that was the point there. The next one along is going to be my 2 pi by 9. Does that make sense? Anybody want me to go through any bits of that again?
When you drew the E graph, you said it never equals 0. So how could you, when you factorized E out, how can you make that equal 0?
You can't make it equal to 0. That's not going to happen. So when you factorize it out and put it as these two things timesing together to equal to 0, when is that going to happen? Because the E part of the equation can't equal 0, then that's like not a solution. I mean, I wrote it down there, but you shouldn't, because that's not going to happen. You know that the whole thing, because you factored the E term out, is only going to equal 0 when the cos and the sine bit is equal to 0. So that's why we could just forget the thing on the front and just work with the trig.
Okay.
Yes, that makes sense. So that you do that quite a bit, and it's, you know, it's making it equal to 0. It's just another adaptation of what you did when you were like in year 9 and you were doing quadratics and you're factorizing and it's equal to 0, and then it's the opposites of the brackets, isn't it? It's only going to happen because the E part can't equal 0. It's got to happen. So that led us to do all that trig, solving those equations to get the 2 pi by 9. Yeah, is that okay? Right, finding the equation of the normal at the point where x is equal to 0. So we can see here x is equal to 0. At x equals 0, y is equal to 0. When we're trying to find the equation of a straight line, we need a point, but we also need the gradient. So we're going to be using y minus y1 is equal to mx minus x1. Now, when x is equal to 0, we need to go back to our gradient function and find what the gradient is when x is equal to 0. So back into this equation here, and we've put x is equal to 0. Now this time the e term on the front will work for us, because when x is 0, anything to the 0 is going to be 1, and then it's going to times by. Where on the cos graph, when you've got cos of 3 times 0, which is the same as cos of 0, that's going to be 1, and times by the 3, and then plus the sine of 0 is going to be 0. So the gradient of the curve at this point, we can see is going to have an m is equal to 3. So the gradient of the normal makes a 90 degrees, so the m of this is going to be minus a third. So just put it back in here, because we know it goes through this origin, it's just going to be y equals minus a third x. So perpendicular gradient there for the normal. Is that okay? Everyone all right with that one? Yeah, it's easier for 3 marks. Sometimes the next part of the questions are harder, aren't we? That one was okay. That wasn't too bad. Right, next question. What have we got here? Have we got an equation that's got y as the subject? Y is not explicit. We've got an implicit. So we need to do implicit differentiation. We're trying to find the gradient. As soon as we see the word gradient, we know we're going to be differentiating. So we need to do dy by dx, but we're not going to write dy by dx. We just need to go term by term. And then every time we come to y, we're going to differentiate with respect to it, but then times by dy by dx. So to start with, we're just going to get 2 plus, now 3y squared. First of all, you differentiate with respect to y, so that would be 6y. But because it was y and not dy by dx, you then multiply by dy by dx plus, and then this next term is a product. So we use the product rule again. It's going to be first differential of second plus second. Now, when y operates at second, you're not differentiating with respect to it, so you can just write y. Differential of first is going to be 6x is equal to, and then you even have to differentiate here, is going to be 8x. Everyone okay with that? Do an implicit differentiation. If you see one of these, if you've done it a few times, this is like an easier question, isn't it, to just apply the implicit differentiation. And now what we need to do is make the dy by dx as the subject. So dy by dx, take that out as a factor, 6y plus 3x squared. Take everything else to the other side. So that's going to be 8x minus 2 minus 6xy. And then all we need to do is divide by that bracket to get our dy by dx. Is that okay? 6x minus 2 minus 6xy over 6 plus 3xy. Now we want the gradient at the point P. So now it doesn't matter that we've got x and y as top and bottom. At minus 1, 1, you just need to feed them in. And if you feed them in, that comes out to be minus 4 over 9. Everybody should be able to just see, putting minus 1, 1 in, you'll get that it's minus 4 over 9. B, find the equation of the normal again. Well, we've got the gradient at P here is minus 4/9. So the m of the normal is going to be 9 over 4. And we've got our point minus 1, 1. So it'll just be y minus 1 is 9 over 4. X minus minus 1, so it'll be plus 1. Cross multiply and get 4y minus 4 is 9x plus 9. And then just make it nice and pretty. I would leave it in the form it asks you often at A level, and just make it pretty and start it with the 9x being positive. So take these terms to the other side. 0 is 9x minus 4y, and then it'll be plus 13. Everyone okay with that? It's not too difficult, just going over implicit.
Could you go to the last slide for just a second, please?
The last one before this one?
Yeah. Where did you get m equals 3 for this part B?
Because what at x equals 0, we can put 0 into our dy by dx. So e to the 0 is going to be 1. And then putting 0 in here as x, cos of 0 is 1, times it by 3 got us the 3. Sine of 0 is 0. So the m of the curve is just going to be 3. So the m of the normal is going to be minus 1/3. So you
Okay,
put in
I get it.
Yeah, you get it now. Yeah. Okay.
Okay, thank
cool.
you so much.
Okay, no problem. Are we all right with that one? Right. This one now, we've got here a curve in figure 1, and it is a function g of x, x squared, 1 minus x, e to the minus 2x. We've got to show that g dash x, so the differential, is going to be a function of x times e to the minus 2. So again, we have got a product. So what I would do is maybe write it as, let's go up here, y is equal to, because it's 3 things multiplied together, it's easy to just put that x squared in. So x squared minus x cubed, and use that as our thing, e to the minus 2x. So now we need to differentiate. Again, using the product rule is going to be first, x squared minus 3x. Differential of second, e to the x, we need to use the chain rule. It's e to the minus 2x times by a minus 2. So that's first differential of second plus second differential of first. So we'll do the differential of first, minus 3x squared e to the minus 2x. So it's asking us to give it as a function of x and e to the minus 2x. So again, we've got to factorize e to the minus 2x. And then you're going to have a minus 2 times an x squared minus 3x plus a 2x minus a 3x squared. And that will be our function of x. So e to the minus 2x. And then here, this all multiplies out to give you 2x squared minus 5x plus 2. Sorry, I've missed a line. It gives you 2x cubed minus 5x squared plus 2x. So this is our function of x. We all okay with that? Now
Where did the cube come from? If the signs in the brackets, the highest indice was only squared. And we're not timesing in another x.
Oh, I've done first differential of second plus, because I've done that wrong, haven't I? It's first, what did I do here? Sorry, I think my phone buzzed, which shouldn't be here, and put me off. Right, let's do it again. We've got this, it's going to be the first x squared minus x cubed, differential of second, minus 2 e to the minus 2x, plus second e to the minus 2x, differential of first. So that's where our 2x minus 3x squared comes from. So here's where our cubes come from. Sorry, I differentiated them both. So e to the minus 2x comes out, and you're going to get minus 2 into x squared minus x cubed plus 2x minus 3x squared. So that's where you get your cubed from there. And when we've got minus times a minus, e to the minus 2x is going to give us a 2x cubed. And then when you've got minus 2x squared, and then another minus 3x squared is going to be minus 5x squared, just collecting like terms. And then you're going to get a 2x, just that 2x there. Okay, so our f of x here is going to be this function of x here, which is a cubic, and it tells us it's a cubic to be found. Okay, so then it says, hence find the range of g. How are we going to do this? Do we all know what range and domain is? So domain are the input values and range are the output values. So when we're trying to find the range, we need to go up and down the y-axis and look out to see where the graph exists. So it's got us here to this function here, and where the graph exists, this is the max and this is the min. So it's kind of given us a helping hand by differentiating, because we need to know what the height of these max and mins are, because our graph, the range, is all in between these values. So again, we've differentiated with, it's forced us to take that e to the minus 2x out, and then if we equate this to 0 at the turning points, when's that going to happen? It's not going to happen when the e function, because that can't equal 0. It's only going to happen when the 2x cubed minus the 5x squared plus 2x is equal to 0. So how we're going to solve this is we're going to see that we've got an x in each term. So take x out, 2x squared minus 5x plus 2. And then these two things times together equal to 0. Either x equals 0, or we can factorize now because we've got a quadratic. So it would be 2x and x. We need signs to be the same. Negatives are involved, so they'll have to be minus and a minus. Two numbers that times together to give you 2. I think if we put a 2 there and a 1, you can see here you're going to get minus 4 minus another 1. So that's going to give us the minus 5 in the middle. So these three things times together equal to 0. Either x is equal to 0, x is equal to, solving that bracket, a half, or x is equal to 2. So what do these relate to? X is equal to 0. That must have been another turning point, which isn't part of the graph. And here, this must be the x is equal to a half, and this must be the x is equal to 2. Does everyone understand why we've differentiated, we've equated it to 0 to get the x coordinates where the max and min? But in order to find the range, we're not interested in the x coordinates. We want to know what the equivalent y coordinates are at those points. So we have to put in these values back into our g of x. So when x is equal to a half, g of x will give us the y value. So we've got a half squared, which is a quarter. And then 1 minus a half, which is going to be a half, and then e to the minus 2 times a half is just going to be minus 1. So altogether, this is an 8th e to the minus 1, which is 1 over 8e. We'll just put the e on the bottom. Yeah, and then we just need to put the 2 in. So when x is equal to 2, you're going to get 2 squared, which is 4. 1 minus 2, which will be minus 1. And then e to the minus 4. So that is going to be minus 4 over e to the 4. So our g of x has got a range of the minus 4 over e to the 4, because that's the bottom one when x was 2, and then less than or equal to g of x less than to equal, what was the higher one? It was 1 over 8 to the e. So that's our range.
So
No,
does
but-
the range just show the x values or the y values between the maximum and minimum?
the y values. When you've got like a function, you've got the domain and the range. So like forget this question. If I just had like 2, 5 and I was 2x and then a doubling 2 I'd get 4 and 10, then the range are the y values and g of x is equal to the y values. So that's why we need the g of x there. So it's when you're looking at the range, it's where does the y go? So above here, we haven't got the graph. So we needed to find how high this was at the max. So we needed to find the max. It happens at x equals a half, put a half into our function to find what the y value is. And then that will be how high the graph goes. And then this one is how low the graph goes. So to find the range, just go up and down the graph and see like where it exists in terms of the y values. Right, part C, state with a reason why the function doesn't have an inverse. So why wouldn't it not have an inverse? Here you've got to think about what types of functions. You've got two types of functions. You've got one-to-one functions and you've got many-to-one. So how do we find which one we've got? You know you've got a function if you do a vertical line test. So go vertical lines all the way across and it only crosses once. So that means you've got a function. Once you know you've got a function, you then do a horizontal line. And if it crosses twice, which it does a few times on this function, you've got a many-to-one. And only one-to-one functions have inverses. So you would just write because it is a many-to-one function and only one-to-one functions have inverses.
I've never heard of one-to-one or many-to-one. Could you explain that, please?
Yeah. So when you've got, say, y is equal to 2x plus 1, then let's have some input values, say 1, 2, 3, and what will be the output? We're doubling it. So 2, add 1, 3, double it, add 1, 5, double it, add 1, 7. So each of those just goes to one unique value. So that is a type of one-to-one function. And when you've got a straight line, y equals 2x plus 1, then if you do a vertical line test, it just crosses once. So that is a one-to-one. Each of the inputs just has one output. If you have y equals x squared, then if we have minus 1 and 1, they will both go to 1, or you'll have 2 and minus 2, they will both go to 4. So you've got many, and as soon as you've got more than just one, going to one answer. So when you've got a many-to-one function, so we draw the graph, if you do the vertical line test, that tells you you've got a function, but when we do a horizontal line, because it crosses twice, see on the straight line when you cross, it only crosses once, this tells you that you've got a many-to-one. You know, when you do inverse sine on your calculator of maybe a half, your calculator only gives you 30 degrees. It only gives you one principal angle because your calculator knows that inverses need to be one-to-one. So on the sine graph, which is like this, it is many-to-one. So what your calculator does is it just restricts the domain between minus 90 and 90, and your calculator will only give you values because it restricts the domain, because it knows inverses only occur for one-to-one. So we can quickly make a many-to-one function a one-to-one and get an inverse for it by restricting the domain. So if you had y equals x squared, instead of doing both sides, if you just did that side of it, then it is now 1 to 1. If you have both sides of it, it is many to 1. So many to 1 functions don't have inverses. Does that help? Have you done functions yet? Whoever asked for that? Maybe
We
skipped. It's only a
finished
tiny little bit,
school
but you do
apparently,
get,
but
yeah,
yeah, I've just never heard of this one.
yeah. Yeah.
So are inverses just when like all the y values are flipped?
Yeah, you just do the opposite. So if I had y is equal to 2x, then the inverse would be y equals half x. So inverse functions are still functions in their own right, and they have to have input values as x's, the same as going forwards functions. So
But
inverse
why
is
does it being a many to one function mean that there is no inverse function?
because when you flip it round, we go 1 to 1 or we go many to 1, and when you flip it round, it then goes 1 to many, and anything that goes 1 to many or anything that ends in a many is not even a function. So because the inverse function would be, instead of many to 1, it would go 1 to many, so it's not a function. Anything that ends in many, see, there's more maths involved where you have the input functions just getting one unique answer. If the input values get lots of outputs, then there's not as much maths and they're not deemed as functions. So you always need to end up with just one answer in order to have a function. So like a circle, if we drew a graph of a circle, that is a case of many to many, because you'd have that x value has got a y value up here and a y value down there. So that is a many to many function, and that's not going to have an inverse because its inverse is also many to many. See, when you do inverses, whatever it is, many to 1, 1 to 1, they just swap round. And to have a function, it always needs to be something to 1. Yeah, so it's only going to be 1 mark, but that sort of thing in the exam is going to be there. Right, this is the last one on the differentiation one, and then we'll have a look at some integration. So this is more a modelling question. Are we all okay to have a look at this one? So we've got a rare species of primroses being studied. The population of primroses in 2 years after the studies is given by this equation. Part A, calculate the number of primroses at the start of the study. So at the start of the study, T is going to equal 0. So all we need to do is put T is equal to 0, and P, if T is 0, anything to the 0 is going to be 1. So that's just going to be 800 over 1 plus, again, if that is 0, that's just going to be 1 plus 3. So 800 divided by 4 is just going to be 200. Everyone okay with that? Calculate the number of species at the start, so T is 1. Part B, find the exact value of T when P is 250. So we need to put in 250 is equal to function, which is 800 e to the 0.1t over 1 plus 3 e to the 0.1t. Now we're just going to divide by 800. So when we take that 800 down, 250 divided by 800 is 5/16 is equal to e to the 0.1t over 1 plus 3 e to the 0.1t. Now we need to cross multiply and get it clear of fractions. So 5, 1 plus 3 e to the 0.1t is equal to 16 e to the 0.1t. Then multiply that 5 in. And now we can collect the e to the 0.1t's on one side. So 5 is going to be, when that goes to the other side, it'll be minus 15. So that'll just be e to the 0.1t. And then what we can do to get the t down, we're going to take ln. So the ln of 5 is equal to 0.1t. So that is going to be 1/10. So the ln of 5 is equal to 1/10 t. So just take that 10 up. 10, the ln of 5 is equal to t. So it says give it in ln form. So that's 10, the ln of 5. Part C, find the exact value where dp by dt is equal, where dp by dt when t is equal to 10. So we need to use the quotient rule. Can I rub all this off? Skip some more room. So, oops, dp by dt. So we've got a quotient. So going back to the beginning, we've got bottom 1 plus 3 e to the 0.1 t. Differential of top. So you're going to power down 1/10 of 800 is going to be 80 e to the 0.1 t. So that's bottom differential of top minus top, which is 800 e to the 0.1 t. Differential of bottom, well, the 1 just goes out, and we're going to have 3 divided by the 0.1. So that's 3 times a 10th, 0.3 e to the 0.1 t, all over bottom squared, 1 plus 3 e to the 0.1 t all squared. Now, when we tidy all that up and multiply that out, just to speed us up so we can get on some integration, if you tidy that all up, you're going to get 80 e over 1 plus 3e all squared. So that will be when we put the t is equal to 10 in, that is going to be what we get for part C. Now, I think I chose this question because part D is something that's tricky if you've not seen it before. Explain why the population of primroses can never exceed the 270. Now you have to go back to the initial question here, and this is all in the form of these E graphs. And because E is a positive, if you think of exponential graphs, they go on and on like that. So when you're thinking about what's going to happen, you're thinking when t tends towards infinity. As t gets really large, that's where the population is going to tend towards. Now, then when we plot this population against t, with these positive t's, the graph is going to be some form of like that, and it goes on and on and on. So what you need to do is get from a graph that's like that to a graph that has got e to the minus t, because when we've got that minus, you're going to have this sort of graph, and as t gets big, the graph is going to tend towards 0. So what we do here is if we divide all terms, so divide the top and then both terms on the bottom by e to the 0.1 t. So just divide throughout each term by e to the 0.1 t. So once you do the same to every term throughout, then the whole thing remains equal. So dividing the top by e to the 0.1 t is just going to give us 800. And then on the bottom, you're going to get 1 over e to the 0.1 t plus 3. Does everyone understand what I've done there? Just each term, oops, sorry. I have divided by e to the 0.1 t, divided by e to the 0.1 t, divided by e to the 0.1 t. So these will cancel. We'll just get the numbers 803, and then we'll get that term there with the 1. But 1 over e to the 0.1 t is the same as 800 over e to the minus 0.1 t, just taking that up in the numerator, plus 3. So we've kept everything the same because we've done the same throughout. But what we've got now is to a minus, so it's going to be the sort of graph that tends down. So as t gets really big, this term is going to tend towards 0 because e to the minus graphs head down. So this is just going to tend, as t tends towards infinity, to be 800 over 3. And when you do 800 over 3, that comes to 266. So in actual fact, the population is not going to go bigger than 266, and 266 is below the 270. So that is just one mark, a little trick there to divide through by the e to the 0.1t. Any questions on that? Do we understand what's gone on there? We all okay? How are we all doing? Have you had enough of differentiation now? Anybody want to ask any more questions? Is everyone following along? Do you want to put anything in the chat? Has that come through okay? Have you all been able to follow along? What you should have maybe been doing is writing with your pen and paper. And there's quite a few of us in here, so I'm sorry, I've just, rather than letting you all input, it's just going to take too long. We won't have time to get on to the next things. But
Will we
hopefully,
have access to the slides?
yeah, I've sent you the slides without my writing on them. I've sent them already, and I'm recording this so you can rewatch it.
Okay, and where can we access the recording?
I'll put it on YouTube, and I'll just send you a link.
Okay, perfect. Thank you.
Perfect. Okay. Right. Are we all happy? Does anyone want a break? I'll just have a little drink and then carry on with integration. Oh no, I had a parametric one. Well, we'll come back to that if we've got time. Let's go on to integration. So when it used to be the old syllabus, integration could have been up to about a third of your C4 exam before it changed in 2017. Now, integration is still a big, huge topic, and it could be up to maybe 20% of one of the pure exams. There's still going to be a lot of integration. So these are all some of the things that you need to do. You get the by parts formula on the formula sheet. The trapezium rule you also get on the formula sheet, but everything else you need to be doing yourselves. Using the trig identities, you get those compound addition formulae. Often you're going to be using the double angle theorem, so you can derive them from what you get on the formula sheet. So there's lots to help you on the formula sheet. There are some differentials and some integrals on the formula sheet, so you can use them as well. Okay, so when we're integrating, we all should know we're adding 1 on and dividing by the new power. E to the x is going to integrate to itself. 1 over x integrates to ln. Cos x, now sine differentiates to cos, so cos integrates to sine. Sine integrates to minus cos. Sec squared is going to go to tan because tan differentiates to sec squared. Cosec cot, these three you probably haven't committed to memory, but these three are on the formula sheet. Cosec cot goes to minus cosec. Cosec squared goes to minus cot, and sec tan, because sec differentiates to sec tan, then sec tan integrates to sec. So have a look at those and then see if we go on to the next thing. If you can remember, this is what you do get on the formula sheet, these here. And these k's, k just represents a constant. So what you would do with the k, you would just times it by in front. So sec tan, what did that integrate to? That's going to go sec. Good. Sine integrates to. Anyone want to shout out? Just unmute.
Minus cos.
Minus cos. Brilliant. Cosec squared.
Minus cot.
Minus cot. Perfect. Minus cos.
Sine.
Sine. Or minus sine. So cos integrates to sine. Cos, that's going to go to sine. So we've got all these plus c's because this is indefinite integration. Okay, sec squared. What was that one?
Tan.
Tan. Perfect. Cosec cot. You remember that one? That,
Cosec.
minus cosec, nearly minus cosec 1 over x
ln x.
ln of x, or ln x, however you say it, minus sine x. That goes to just cos. The sine differentiates to cos, so minus sine integrates to cos. Okay, cool. So when we are going to be integrating, what we've got to do here is always be thinking of what's going to happen if I took that on top. Now, when you're integrating, you're going to be adding 1 on and dividing by the new power. So that would go to 3x plus 2 to the 0. Well, 0 as a power is okay. It's just going to be 1. But when we divide by 0, that's going to be infinity. So this dividing by 0 causes a problem. So instead of doing that, we have to think of the fact that we've got a version of 1 over x, which does integrate to the ln of x, but we have got 1 over a function of x. So we're going to be using the reverse chain rule. So we know what 1 over x, just thinking of that denominator and leaving it alone in the denominator, that is the ln. So if I write the ln of 3x plus 2, and then think if I differentiate that, if y is equal to that, then dy by dx will equal 1 over the 3x plus 2. But then because I've left alone on the inside, I would be timesing by 3. So when I've integrated, I then just need to compensate for what I'm going to get from the chain rule and divide by 1/3 on the front. So we're considering differentiating the ln, and that will give us 1 over, leave alone, times by the 3. So hence we need to compensate from that 3 that's going to come from the chain rule and put it in the front. So it's 1/3 the ln of 3x plus 2. Is that okay? Do we all understand reverse chain rule? Understand where that third's coming from? So often you're looking at the outside function and integrating with respect to that, and then thinking about what will come from the differential of the inside when I then apply the chain rule to get back to what I've started. So these are all the same sort of thing. So you're seeing you've got a function of a function. When I say the outside function, I mean what happens to x second. If I know what x is, I would times it by the 3 and add 1, do that power function first, and then do e. So always integrate like we were differentiating with the chain rule with respect to the outside. So how does e integrate? It just stays itself, but then you need to compensate and divide by 1/3 on the front. So we're all happy with that. Leave alone, compensate for what will come from the chain rule. Anyone want to do the next one? Do you want to shout out what will happen here?
Times by 1/2. Minus 1/2.
Minus half, but what is the 1 over this linear function on the bottom? What's the outside?
Is it minus 1/2 times ln 1
Yeah, it's minus 1/2, because just consider the fact that we've got a denominator 1 over x, so kind of leave it alone and then compensate on the front. Right, does anyone want to do the next one? Integrate with respect to the outside. So what happens when we integrate? We add 1 on and divide by the new power. So you would leave alone on the inside. Anyone want to have a go at it?
Wait, no, this is integrating.
Yeah. So just did a
Can we
load
go
of.
through this one together?
What did you say? Sorry.
Can we go through this one together?
Yeah, certainly. Yeah. So when you're integrating, you add 1 on and divide by the new power. So we're going to think about this outside function. So we need to add 1 on. So my first guess will be leaving alone, add 1 on, and then divide by the new power. So that's just treating this as if it was just x. But then because it wasn't x, I then need to think about when I differentiate. When you differentiate, you'd power down, which would get rid of that 6. You'd take 1 off to 5, but then you'd times by a -3. So we need to compensate for that and stick a minus a third on the front. And then when we put a minus a third on the front, they're going to times together to give us the 18. Does that make sense? Now before, when we had sec tan and just single x, that integrated to sec. So thinking about the outside function, it's just going to be sec 3x, but then we're going to also times by 3 from the chain rule when we differentiate. So we need to get rid of that and put a third on the front. Do they okay,
So
everybody?
when we have a 1 over something, we have to like pretend to differentiate the denominator and then see what we need to divide to compensate.
Yeah, so whenever you're doing these, I always try to think about outside, inside. So if we just look at this one, maybe easier. If you think of this is something we need to think about, and this is something we need to think about. Look at the outside first and pretend the inside is just x. How would we integrate if it was just x? You'd go 4 minus 3x, because it's not x, so we need to write it again, and then we'd add 1 on and we'd divide by the new power. That's us integrating with respect to the 5. Now, if we had y is equal to that, if we differentiated, what would happen? We'd do the chain rule, we'd power down, which would get rid of that 6 that's just gone on the front, and we'd go to the 5. But then from the chain rule, we've differentiated with respect to that. We then times by the differential of the inside, which is a -3. So we need to get rid of that -3 on our integral. So we need to times by -1/3. So you're getting rid of what's going to come from the chain rule, and then you can join those both together. So what's going to come from the chain rule is the differential of the inside. When you're differentiating, you're often powering down and timesing something on the front. When you're integrating, you're always putting something underneath. Does that help explain what's going on?
Yeah.
Yeah, are we okay? Yeah. So like I keep saying, this outside, inside, once you crack that and kind of just get to grips with that, I don't know whether I'm confusing you by saying outside, inside, whether how you've been taught at school or whatever, but that's always helped me to just think that outside, inside, everything needs to be compensated for or allowed for, and you're just going to do one thing at a time, but always work from the outside in when you're using the chain rule and when you're integrating, do reverse. Okay, let's have a look at this next question. So we're using trig identities. So when you've got sine squared, you can't integrate when you've got just sine squared. We can't, there's no rule for adding 1 on divided by the new power. So what we need to do is use a trig identity. So in the exam, it's not going to tell you to use a trig identity. You need to know that that's what you've got to do. Anybody know the trig identity I need to use to solve this one?
Cos squared -1?
No, because if I use cos squared, I can't integrate either.
Cos 2x equals 1 minus 2 sine squared x.
Yeah, brilliant. Cos 2x is equal to 1 minus 2 sine squared x. Now, if you can't remember that, on the formula sheet, you get cos A plus or minus B is equal to cos A cos B minus plus for cos sine A sine B, which is equal to, when A and B are the same, cos squared A minus sine squared A. And then all you do is replace the cos squared with 1 minus sine squared, and 1 minus sine squared minus another sine squared will give you that. So that is the double angle formula, and we do know how to integrate when we've just got a multiple of x there on the front. So now we need to make that sine squared the subject. So if we take that to the other side, it's going to be 2 sine squared x is 1 minus cos 2x. And then sine squared x is equal to, divide by 2, a half minus half cos 2x. So we're going to
How
be
did you derive it again from the equation sheet?
Did you understand that bit there, the first bit? Because A and B are the same.
Yeah.
So then all we need to do to get a version of cos 2x that's just got sines is replace that cos squared A with, we'll do it here, 1 minus sine squared A, which is cos squared, minus another sine squared A is 1 minus 2 sine squared A. So you're just replacing that one with the 1 minus sine squared. And then you've got 2 of them.
Okay.
Did you follow? Yep. And then all we've done is made that sine squared the subject and taken everything to the other side. So instead of integrating sine squared, we're going to integrate a half minus a half cos 2x. And we need to go pi by 12 to pi by 8. So now it's easier to integrate. We just integrate term by term, move along the bus. So half integrates to a half x minus. Now when we're integrating cos 2x, cos is the outside function. That's going to integrate to sine 2x. But we have to integrate with respect to the 2. Or we have to compensate or what will come from the chain rule, which will be a 2. So we need to put another 2 on the front. This half's just going to join in. We're going to get a quarter sine 2x. We've already integrated, so you need to have your square brackets. Pi by 12 to pi by 8.
When we integrate the cos, are we integrating positive cos or negative cos?
I've left the minus, so I've put the minus there. So I was just integrating positive cos. Cos integrates to positive sine. Yeah, everyone happy with that? So I've used the reverse chain rule to get that quarter on the front. Then we need to put in our limits. So pi by 8, half of that is going to be pi by 16 minus a quarter. Now, when we double pi by 8, we're going to get pi by 4, and sine of pi by 4 is the same as sine 45. Your special triangles or on your calculator, it's 1 over root 2. So that's the top limit in. Pi by 12 is going to be 1 pi over 2 12s are 24 minus a quarter. So when we double pi by 12, we'll get pi by 6, which is 30 degrees, and sine of 30 is a half. So it's really useful to know those exact values, or you can just use your calculator. And then this, when we sort it all out, will give us that pi by 48, because we can see putting these with a common denominator, that's going to be 3 pi by 48. And we've got a minus 2 pi by 48, just doing those two terms. And then the rest of it, we've got minus 1 over 8 root 2 minus or plus for that minus and minus 1 over 8. And then if we just give that a root 2 over root 2 to get a common denominator, or no, I think we'll just rationalize the denominator, you're going to get to there. Okay, hopefully you'll be able to sort that one out and get to there. Let's have a move on and go to here. Now we've done some reverse chain rules, but this is of the function where we've got f dash x over fx. So we've nearly got it, because on the top, what we're looking for is to have a 3x squared. Now, if I've made that 3 times as big, I'll need to compensate and put a 3, because whenever you integrate this situation, it's just going to go to the ln of the f of x. because the differential is going to come from the chain rule. So once you've got that situation, you don't need to worry about the differential on the top. This is just going to be 1/3 the ln of x cubed plus 1. And then think about differentiating. You would do 1/3 1 over the x squared, x cubed plus 1 times the differential of the inside, which would give you the 3x squared, and then those 3's would cancel and you'd get back to your question. So this is reverse chain rule. We've already done quite a few of those ones. So hopefully that makes sense. Anyone want to have a go at these then? These are reverse chain rule as well.
Could you go to the last question and just explain it quickly again, please?
Yeah, have you met this function before where we've got the differential sitting on the top of the main function underneath?
No, I haven't seen that before.
Okay, so that is going to always differentiate to just ln of the bottom. So why does that happen? So what you're wanting to get is the differential on the top. Is the differential sitting on the top? What is the differential of the bottom?
Just 2 x squared.
No, the differential of the bottom, if you've got y equals x cubed, what will dy by dx be? Power down 3x squared. So the differential we want to have sitting on the top, we want a 3, but by putting a 3 there, you can adapt your questions by a constant. But if I've made my question now 3 times as big, I need to put a 1/3 on the bottom. So they will act to cancel each other. So now when we have a constant on the front, that's just going to join in. When you've got y is equal to 3x to the 4, anything on the front, whether you're differentiating or integrating, is just going to join in. So that 1/3 is going to join in. And when we've got this situation, it's just going to be the ln of the x cubed plus 1. Okay, so that's my answer. Now you can always check you've got it right, because if you look at your answer, when I differentiate that, will it get back to my question? So if y was this answer and I wanted to differentiate, what would I do to differentiate? I would use the chain rule, because I've got a function of a function. Again, the 1/3 is just going to join in. Differentiate with respect to ln would be 1 over, leave alone on the inside, and then times by the differential of the inside, which would be the 3x squared. So then these 3's would cancel, and I have just got back to my original question. So when you've got this situation with the differential on the top, you don't need to worry about that. You just need to do the ln of the bottom, because it's a function of a function. The top will come when you do the reverse chain rule working backwards. Does that make sense?
Yeah, thank you so much.
Yeah, okay, no problem. Okay, do you want to have a go at these? These are the type where we've either got f dash x over fx, which we've got here, so that's going to be ln's, or we've got here f dash x fx. So here, have we got the differential sitting here? We nearly have. What we want is a 2x, but because we've made it twice as big, we need to compensate. So this half's going to join in. So whenever you've got this situation, you don't need to worry about the differential of the inside. You just need to integrate with respect to the 3. So this is going to be a half x squared plus 5 to the 4. Add 1 on, divide by the new power, which is going to join in with that. And then will that do it? If I think about differentiating that, the 4 will come down. I'll leave alone, I'll take 1 off, which will get me back to the 3. Then I'll times by the 2x, which will come on the front, and then that 2 will divide there by that one. So altogether, this is going to be 1/8 x squared plus 5 to the 4. Yeah. So here, this is the same situation. This cos is f dash x, and then we've got a function of x. So of the main function, we need to think about the outside one first. So that's why we're considering sine cubed. We're adding one on and dividing by the new power. So we'll go sine cubed x and then a third. So by the chain rule, we'd power down, take one off. That is leaving alone on the inside, and then we times by the differential of the inside, which is cos x. So that cos is going to come when we work backwards using the chain rule. Then this last one, because we've got this in the denominator, we've already got the differential. We don't need to do any compensating. This is just going to be that. But on all of these, we need to have our plus c's as well. Are we okay with that? Integrating by inspection using the reverse chain rule. Right, hopefully we've got some questions now. Okay, so here's some exam questions. 8 marks for doing this one. So we've got a curve here, shows the curve with this equation. The curve meets the x-axis at the origin and at the point A. Find in terms of ln of 2 the x-coordinate of the point A. So what's happening at the point A? On our graph, this would be a coordinate A, 0. So y is equal to 0. So if we let y is equal to 0, 0 is equal to 4x minus x e to the half x. So what are we going to do now? Again, like we had with our differentiation, equal to 0. Whenever you've got those zeros, look to factorize. What can factor an x out? 4 minus e to the half x. So 2 things timed together, either x is equal to 0 or 4 minus e to the half x is equal to 0. So that x equals 0 is obviously this point here, not the one we're after. We're going to have to just solve this second one. 4 is equal to e to the half x. So ln of 4 is equal to half x, and then cross multiply 2, the ln of 4 is equal to x. Now it wants it in the form ln of 2. So how can we sort this out? 2, the ln of 2 squared, which is 4, and then that 2 by our log laws can come down. So it's going to be 4, the ln of 2. Everyone okay with that? So that is the x coordinate for the ln of 2. Right. Part B. Where's my pen gone? Part B. Find the integral x e to the half x. So this isn't the whole curve. This is just part of the curve, but it's asking us to integrate. And here we notice that we've got a product. What is the product rule for integration? It's going to be by parts. Have we all done by parts? So you get the formula on the formula sheet, but you do by parts usually later on in your syllabus because you have to have your wits about you because you need to be integrating and differentiating in the same question. And what we do is we choose one of the terms to be u and one of the terms to be dv by dx. Now, anyone know what we do to decide which one is which? We use an acronym.
Right.
Late, perfect. So we do logs, algebra, trig, exponentials. So we have got some algebra and some exponentials. So this is telling us to, because a comes first, that u is going to be x. So therefore dv by dx is equal to e to the half x. Now to get the by parts formula, you need to differentiate this one. So du by dx will equal 1, and you need to integrate this one. So when we integrate, we're going to leave alone and then times by the, think about the differential that will come. And so what we need to do is compensate for the fact that our half will come from the chain rule. So we need to have a 2. Then the by parts formula is uv minus the integral of the bottom 2. So that's going to be 2x e to the half x minus the integral of 2 e to the half x. So 2x e to the half x minus, now this is something we can now integrate. So the 2 is just going to join in. We're going to get e to the half x again, but then it's going to times by 2 again. So we'll have a 4, and that will be us plus c. Everyone okay with by parts? You do get it on the formula sheet. So I just make that little box thing going on. Use the acronym LATE. We all heard of that before. That tells you to decide what's going to be u. The other one's got to be dv by dx. One you have to differentiate and one you have to integrate. So in this question, it's asked us to do that integral because in part C, we've now got this region R is bounded by the curve and the x-axis. Find by integration the exact value for R. So we need to be integrating R.
Can you explain the acronym again, please?
So LATE, this stands for logs, algebra, trig, and exponentials. So
How do you know when to use them or which one goes
so
with
this
what?
tells you what is going to be u. So that's the first thing that we're going to write down. So you look at the two things that are being times together. It's the x or the e to the half x. So you've got a product between those two. And then of the two things that are being product, we've got in our question algebra and an exponential. So because algebra comes first, that tells us that the u has to be the x. So the dv by dx has to be the other thing. So the acronym just tells you what's going to be u. So once you've decided and split your by parts in the two terms, what's u and what's dv by dx, one you have to differentiate and one you have to integrate. And then the by parts formula is just uv, so that's why we did those two times together, minus then the integral of these two times together. And that's on the formula sheet. Is that okay? Yeah, does that help you decide what to do? So now we need to do our integration. So we need to be integrating our curve, which is 4x minus x e to the half x. And we're going between, because we know we're going from 0 to what this made us find in part A, 0 to 4, the ln of 2. So now we just need to integrate. So that's going to be 4x squared all over 2 minus, now it's made us in part B integrate this by parts, but when we did by parts it gave us these two terms and it's minus an integral that has got two terms, so we need to have some brackets and then just slot this stuff in. We won't do the plus c, so it'll be 2x e to the half x minus 4e to the half x. And we need to go from 0 to 4, the ln of 2. Now, when you put all your limits in, I'd maybe leave you to do that and try and crack on and do some more. Got some partial fractions questions. Got a couple more questions to try and get through, not long. But when you put your limits in and get it in terms of ln of 2, it all comes out to be 32, the ln of 2, the ln of 2 minus 1 plus 12. So you can have a go at integrating that. Right, next one, partial fractions. Express this in partial fractions. So that's going to be a over x minus 1 plus b over 3x plus 2. And then we can go clear of fractions. So our 5 is going to equal a into what it's not got. Hoping everyone's fine with partial fractions because that's relatively straightforward part of the course. And then we just let x equal various things. I would just let it equal the easier one first. If x is equal to 1, you'll get 5 is equal to 5a, which tells us that a is equal to 1. Let x equal what will unravel for that second bracket, minus 2/3. So 5 is equal to minus 5 over 3b. So that tells us that b is minus 3. So it should be okay to find that. Hence find the integral. Now sometimes it just gives you this and you need to know to put it into partial fractions, but this question kind of gave you a helping hand because splitting it up into partial fractions, you had a 1 over x minus 1 minus 3 over the 3x plus 2. And now we can just do it term by term. So integrating this is 1 over here, it's the ln of x minus 1. And then minus 3, the ln of 3x plus 2. But then thinking about compensating for the chain rule, we're going to have a divide by 3. So they're going to cancel. And then we're just going to have plus c. Part C, examiners seem to like partial fractions, and if it's with a differential equation question, usually the partial fractions part is more straightforward because now we've got to solve the differential equation, and we've got this here. So what do we do when we're solving differential equations? We can see that we need to get all the y's on one side and all the x's on the other side. So times in both sides by dx and taking the y down, you're going to get the integral of 1 over y dy is equal to, we need to leave the 5 on the other side because then we bring those brackets down. That is going to be something that we have just integrated and got all that. So integrating on the left, the ln of y is equal to, we've just worked out that integral. It was the ln of x minus 1 minus the ln of 3x plus 2 plus c. And what can I do with that c? That c is just a constant. I'm going to write that constant plus the ln of k, because then I've got everything as logs, and I can say the ln of y, because all these terms are now logs, we can just do it as a single log. The x minus 1 and the k, they're both plus, so that's going to be the ln of k times x minus 1, and then because this is minus, that's going to go underneath. And then because we've just got them as single logs, we can just ditch the ln's on the front and say that y is equal to all that. Now it's asking us for a particular solution because we've still got a constant. That's a general solution. For a particular solution, we need to put these values in. When 8 is equal to y, we've got 8 is equal to k, and x is 2. 2 minus 1 is 1, and then 2 times 3 is 6, plus 2 is going to be 8. So k is equal to cross multiply 64. So our particular solution is y is equal to 64 x minus 1 all over 3x plus 2. Are we okay with the differential equations? Any questions on that one?
Why did you write integral of 1 over y? Where did that come from?
Okay, so you've got this dy by dx, which can either operate as a derivative on top of each other, or they can operate at the, when we have an integral sign. So you need to have the dy by dx in the numerator position. So you need to cross multiply and take that dx up, but that means that all the y terms need to be on the left. So that y needs to cross multiply and come on the bottom. And then all this brackets needs to cross multiply and come under the 5. So you're just cross multiplying. So because you now separated your dy by dx, you need to separate the variables and integrate. So either this dy by dx is written on top of each other, or they're written when we have an integral sign. So I've cross multiplied, separated the variables, and then integrated both sides. The dy just on the end can never operate by itself. It either operates with an integral sign or it operates over with a dx on the bottom.
Oh, okay.
Have you done
Thank you.
differential equations yet? That it is probably a topic that's at the end of the course, so you might not have met it yet.
We did integration, but we really rushed it so we could get on to the stats and meg.
Right, okay. So this is at the end of the integration section, the differential equations. Now you'll know we've got a differential equation. It usually tells you in the question there, but you know you've got a differential equation if you've got an equation that's got dy by dx, and then that's how to do it. You separate the variables, keep the dy by dx in the numerator positions, so that dx needed to come up, and you need to have all the x terms on one side, all the y terms on the other side, and then you just integrate both sides. You do have an integration constant both sides, but you just lump them together all on the one side. So that integration constant on the left, you just lump it in with the one on the x side. Yeah. Okay, so you need to look over differential equations again if that's something that you've forgotten. Okay. I think got time for maybe one more. We've got here parametric integration. So x and y given parametrically. For part A, we've got to show that A has the coordinate 0, 3. So we can see A here is on the y-axis. So 0, 3 means that the x coordinate has to be 0. So if we let the x coordinate equal to 0, 0 is equal to 1 minus half t. Half t is equal to 1. So t is equal to 2. And then how do we find what the y coordinate is? We need to put that t equals 2 into the y equation. So y is going to be 2 to the t equals 2, so squared, minus 1, which is 4 minus 1. So that is going to be 3. So that's how to show that the a coordinate is 0, 3. Then similarly, find the x coordinate of the point B. So what's happening at B? We've got something 0. So this time the y coordinate is 0. So if we let y equals 0, 2 to the t minus 1, and put 1 on the other side, 2 to the t. What's going to happen there is going to be when t is equal to 0, and then put that into the x. So x is equal to 1. So this is the coordinate here, 0, 1. Or 1, 0, sorry. Yeah, everyone's following so far? Any questions? No? Find the equation to the normal to C at point A. So the normal is an equation of a straight line. So we need y minus y1 is equal to mx minus x1. Now I've already got what the coordinate is. It's 0, 3, but we're going to need the gradient. We need to find the m. So when we're given parametrically, we have to differentiate each and make a chain. So dx by dt is going to be 1 minus a half. No, not sorry. 1. Lost concentration there. It's just going to be minus a half dy by dt. Anyone know how to differentiate when we've got 2 to the t. You remember how to do that one? Doesn't come up that often, but it's like a tiny part of the course. We'll go over that. If y is equal to 2 to the t, what you need to do is take logs to both sides. The ln of y is equal to the ln of 2 and bring that t down using your log laws. Now you've gone from an explicit equation to implicit. Remember when we did implicit differentiation before? You differentiate with respect to y, which will be 1 over y, and then because it's not y, you need to write times by dy by dx. And then what's the differential of this side? This is just a constant times t. So how do you differentiate like 3x? It just goes to the constant. So this will be the ln of 2. And then dy by dx, just cross multiply, take that y up, is y, the ln of 2. And then what was y? Y was 2 to the t. So this is 2 to the t ln of 2. So whenever you've got this situation, you know that e to the x differentiates to e to the x. So it's a little bit like that. Because you've got that term in the air, you're going to say it's 2 to the t, but because it wasn't e, just got to remember that it's got to be times by the ln of the base. So that's what the dy by dt is going to be. And then we just need to do dy by dx, which will be dy by dt times dt by dx, which is dy by dt 2 to the t ln of 2 times upside down of this, which is just going to be minus 2. So what we need to do is put in that our t at the point A. What's our t? T was going to be 0 at A. We've got 0, 3. So an x is 0. What's our t going to be? So at A, t is equal to 2. We had that before. So just putting t equals 2, that's going to be 4 times the minus 2. So that's going to be minus 8. Oops, sorry. The ln of 2. So putting that into our normal, we're going to get the L of the normal is going to be the negative reciprocal. So that's going to be 1 over 8, the ln of 2. And then putting it in here, we've got y minus 3, because remember we're at the point A, is equal to 1 over 8, the ln of 2, and then of x, because x1 is 0. So you can just rearrange that. And then for part D, we've just got to use integration. So last bit, we'll just do integration. Now, when we're doing parametric integration, what you've got to do is you're integrating between here. This was -1, and we found b to be 1 of y dx. But what we do in terms of the t is we need to change these limits. We can integrate with respect to y, but in order to then integrate with respect to t, if we do dx by dt times dt, these things will stand to cancel and we will just be finding x dx. So changing the limits, when x is equal to -1, then putting it in here, we'll get that t is equal to 4. When x is equal to 1, we'll get that t is equal to 0. We've already had that. So we are going between 4 and 0. So you have to keep these, even though they're the wrong way round, you have to put them in the right place. And t was -1, it was 4. So they're kind of the wrong way round. And we're doing y, which is this here, 2 to the t -1 times the differential of x, which was -1/2, and then dt. So now we've got to integrate 2 to the t. So like what we've just done over here when we did ln's, when you're doing the integral of 2 to the t, remember it's a little bit like the chain rule, you have to compensate. Here we times by the ln of 2. So when we integrate, we're going to do 1 over the ln of 2, 2 to the t. And then the -1 of and then we'll just have minus t, and the half's just going to join in. I can put that on the front, and we're going between 4 and 0. Now because we've got this -1/2, what we can do is change that to plus and change these round. So it's 0 to 4. Now when you put all of this in, just to finish off quickly, maybe leave you to fathom all that out, what you're going to get as your final answer is 15 over 2 the ln of 2 minus 2. Okay, I think I did have one more by substitution, but I think we've ran out of time there, and I've run out of steam a little bit getting towards that end. So if we leave it there, and I'll send you the link to the video of this so you can re-watch anything, and you have got the questions, which are just the bare questions that on a PowerPoint that you can have a look at and see if you can then redo them. So that's a good idea if you look at these questions and then see if you can do them again now that we've just gone through them. But hopefully that's been a good whistle-stop tour through calculus, through your differentiation and your integration. So
Oh, I have a quick question. Could you go back onto the slide we were just on, please?
Yeah, okay, 1 sec.
At the very top, you times dt to the integral, but where does that come from? Do you just
Yeah, when you are integrating, so in order to find an area, what do? You integrate between a and b,
yeah.
y dx. Now, you know when you do the limit as a sum, this integral sign means add up. And what you are doing when you integrate is you are integrating loads of strips. So integration from first principles, a strip is dx wide. And how high are the strips? They're all y high. Now, as this curve goes up and down, they're all different heights. So one strip is y high and dx wide. Yeah? So when you integrate and add your power on and divide by the new power, all that business of doing that manipulation is equivalent to you finding the area of all these strips. So you don't actually do anything with that dx, but it needs to be there because these two times together represents the area of a rectangle because they're the dimensions of the rectangle. So to find an area under a curve, you must have y and then the dx. But because we've got it parametrically, what we need to do, our y is going to be in terms of t. So we need to integrate with respect to t on the end. But what we'll need to do in order to get an area under a curve, because it must be dx. So what you times by is dx by dt. So you're going to times by the differential of the x side of the equations. And then you can put dt. And then if you do the y in terms of t, you then multiply it by the differential of the x, then these dt's will cancel, and we are in fact just integrating y dx, and therefore we are finding the area under the curve between the x-axes. So that's why when you do parametrically, you must have y, and then you must also times by dx by dt, because then that allows you to integrate that y with respect to t. You must times by dx by dt before you do it. Does that make
Oh,
sense? Does that
Uh,
do
yeah, kind of.
kind of?
When you right next to the bit on top, you wrote when x equals -1. Which equation did you substitute those x
So
values?
go in here to find the t value. So when x is -1, you've got 1 minus, you've got -1 is equal to 1 minus half t. So then
Yeah.
take that to the other side. Half t is equal to, take that to the side 2, and then just double up. T is equal to 4.
Oh, okay.
So just plugging it into the x side of the x equation.
Okay. And last one, sorry, but when you wrote the bit with the square brackets right under the graph, you changed the position of the 4 and the 0. Why
Yeah.
did you do that?
Yeah, because when you have had a minus here from this -1/2, can you see these limits are back to front? When you integrate, say I integrated normally, and I'm going maybe from 0 to 1, and I can see that the area is above, so whatever it is, dx, I'm going to get a positive area. If I swapped them round and had the 0 to 1, when I do my brackets, because I'm putting the top limit in first and the second, I'm going to swap them round. I'm going to get a minus of when I put them the right way round, because you'll be putting the limits in back to front, and so therefore you'll get a minus. So if you've got a minus on the outside, you can just swap the limits, and then they will interchange, and it will just allow us to put the top limit in first.
Oh, okay. Or you could just leave it the way it
Or
was.
you could
and-
just leave it the way it was, yeah, but that's just another little trick that you can do. There's loads of little
Oh,
tricks like that, isn't there?
yeah. Okay,
Yeah.
thank you so much.
Okay, right, guys. Hopefully that's all made sense. Sorry there's not been chance to join in so much, and you've just all just listened to me, but there's a lot of us, but hopefully you'll be back tomorrow. Tomorrow it is stats for 2 hours tomorrow, so we'll have a go through that, and then mechanics on Wednesday. Okay, everyone, so hopefully I'll see you tomorrow. Thanks for
Thank you.
joining
Thank you.
very much. Thank you.
Thank you.
Bye
Thank
then.
you.
Bye, guys.
Thank
Bye.
you.
Bye. Bye.